In this video, I'm going to talk a bit about energy and thermodynamics. So energy can be broadly classified in two different ways. We can have kinetic energy, which is the energy of motion, and potential energy, which is the energy that's determined by the position of an object or the chemical composition of an object. And so the potential energy is how much energy you could get out of the system. You can think of it as stored energy, where kinetic energy is energy that's actually being used by the system or gained by the system. And so that's the energy of motion. Another way we can classify energy is by both work, which we can think of as ordered energy, and so this can also be thought of as energy that can be used to move something in a meaningful way. So for instance, when you use energy in your vehicle, you're using the chemical energy that's in the petroleum, and so that's actually causing the movement of the vehicle. So that's a meaningful movement of stuff. Your vehicle moving in a particular direction is a meaningful movement of that stuff. But we also know that when we burn it, that we get heat from it. That's thermal energy. This is disordered energy. And so this is the translations, which is sort of straight line motion, rotations, and vibrations of particles. And so the greater the motion of particles, the greater the heat. And heat flows between objects. So you know that if you were driving for a while, you open up the hood and you try touching the engine, it's going to feel hot. So that means that the heat is flowing from the engine into your hands. And so that heat is never destroyed or created. It only flows from one thing to another. And so that is the first law of thermodynamics. And we also have the unit of energy, which is the joule. That's the SI unit of energy. And this is defined as a kilogram times meters squared over seconds squared, which you can think of as the amount of energy it takes to accelerate 1 kilogram over 1 meter. We also have the unit of calories, which is equal to 4.184 joules, and we will see here in a little bit why that is the case for that. We can also have kilojoules, which is just defined as 1,000 joules. So again, using that kilo prefix tells us that we have 1,000 of the base unit, where the base unit here is the joule. So temperature is the average kinetic energy of all the particles in the system, and so we see that that is related to the velocity of all the particles in the system. So this includes energy from vibrations, rotations, and translations. And the warmer something is, the higher the average kinetic energy of all the particles in a system. So if we look at a graph like this, which is called a Boltzmann distribution, we see that we are looking at the velocity of the particles here on the x-axis, and then the proportion of particles that have that velocity here on the y-axis. And so we see that at the 100 Kelvin temperature, that the average velocity of particles is under 2,000 meters per second. Whereas if we increase the temperature to 300 Kelvin, then the average velocity of the particles is over 2,000 meters per second. And if we increase the temperature to 1,000 Kelvin, then the average velocity of the particles is approximately 4,000 meters per second. And so what we see is that increasing the temperature increases the average velocity of our particles in the system. And so heat and temperature are often used interchangeably. The words heat and temperature are often used interchangeably in everyday conversations, but in science they actually have different meanings. So remember that heat is the total amount of thermal energy in a system, while temperature is the average energy of all the particles in a system. And we also have that if we have more heat in one system, so in system A right here, and then we have less in system B right here, if we put those two things together, then the heat will transfer from the system A to the system B. So from the warmer system to the colder system. And so that means that over time their temperatures will become equal to each other. And so when we are thinking of temperature, we also have different ways of measuring this. We have these different scales for the temperature. We have Fahrenheit, Celsius, and Kelvin. And if we have the different units for it, that means we want to have different ways of converting between those units. So these are the formula for converting between Celsius and Fahrenheit. And then we have this for converting between Celsius and Kelvin. And so for the units in these constants, the 32 and the 1.8, You often see these formula without the units actually shown explicitly, but these are the units you can use if you are trying to solve these by canceling units. And so the 32 has degrees of Fahrenheit, and the 1.8 is degrees of Fahrenheit per degrees of Celsius. And I also consider these definitions, so I do not actually count these towards these significant figures when you are doing these conversions. And this factor of 1.8 degrees Fahrenheit per degree Celsius is just because there is 1.8 degrees of Fahrenheit for every 1 degree of Celsius, meaning that a single degree of Celsius is bigger by 1.8 than a single degree of Fahrenheit. And so we have to have that factor of 1.8. So you can actually read this as we have 1.8 degrees of Fahrenheit per 1 degree of Celsius. Then the 32 degrees Fahrenheit is just because the two scales have a 32-degree difference between their zero temperatures. And then when we're changing between Celsius and Kelvin, we can think of it something like this, where we have this conversion factor of 1 Kelvin per degree Celsius, or 1 degree Celsius per Kelvin. And what that tells us is that the size of a degree Celsius is equal to the size of 1 Kelvin. So we can think about it like this, that 1 degree Celsius, the magnitude of that change is equal to 1 Kelvin. And also note that on the Kelvin scale, we do not use the degree sign. So in other words, you would not say that something is 300 degrees Kelvin, but instead just 300 Kelvin. And note too that in this class, we're using 273 as the conversion factor. In reality, it's 273.15, but in this class, we will not be using the digits after the decimal. And so here is an example of how we can do this. So say a patient comes into the doctor's office with a temperature of 102.5 degrees Fahrenheit. What does this correspond to in degrees Celsius? And so I'll let you work on this before I show the answer. And so what we get is that we use this formula here, so 102.5 degrees Fahrenheit minus 32 degrees Fahrenheit. Then we divide that by the 1.8 degrees Fahrenheit per degree Celsius, and we end up with 39.17 degrees Celsius. And we see that this is going to be in 4 significant figures, and so that's because the measured value here is 4 significant figures. In thermodynamics, we also have this concept of the specific heat. So we can think of this as the amount of heat in joules or calories needed to change the temperature of exactly 1 gram of a substance by exactly 1 degrees Celsius. And this is a physical property. And this is actually the formula for it. So SH here for specific heat is equal to Q, which is just the heat transfer, divided by M, which is the mass, times delta T, which is the change in temperature. And this will have units of joules over grams times degrees Celsius. And so we can use this equation here for the specific heat to derive the heat equation, which is this. So if we want to know how much heat is being transferred from something, we can use this formula right here. Different substances will have different specific heats. These are physical properties of these substances. And specific heat, we've been calling it SH. It's usually denoted C, quite often C with a subscript P. And so what we see, like I said, is that these different substances can have different specific heats. So air, for instance, is 1.0035, aluminum 0.897. We can go down here to water. That's the 4.18, and then this has 1.3 here. It's usually 4.184, and so as we saw earlier, that is how the calorie is defined. And so what we see is that metals, for instance, usually have very low specific heat, so that's why they heat up fast. So we can think of specific heat, like I said, as the amount of energy that needs to be put into 1 gram of a substance in order to increase it by 1 degree Celsius. So for instance, what does it mean that water has a specific heat of 4.184 joules over grams Celsius? So I'll let you think about this and try to answer it on your own. And so what this means is that it takes 4.184 joules of energy to warm up 1 gram of water by 1 degree Celsius. So for instance, if we have 1 gram of water in a beaker here, and it's at 25 degrees Celsius, then we have to add 4.184 joules of heat in order to bring this 1 gram of water up to 26 degrees Celsius. So we're raising the temperature of 1 gram of water by 1 degree Celsius by inputting 4.184 joules of heat. Another practice problem here, so what is the specific heat in joules over gram degree Celsius of sodium if 92.3 joules is needed to raise the temperature of 3 grams of sodium by 25 degrees Celsius? And I'll let you work on this before I show the answer. And so the answer to this is that we use this, so that's the specific heat equals the heat transferred divided by mass times the change in temperature. And so in this case, we plug in the numbers. It's 92.3 joules over 3 grams times the change in temperature, which was 25.0 degrees Celsius. And so this would actually have a specific heat of 1.23 joules over grams Celsius. And so if we heat 7.77 grams of water, which has this specific heat here, 4.184 joules over grams Celsius, from 25.3 degrees Celsius to 29.4 degrees Celsius, how much energy was transferred into the water? And so I'll let you think about this and try to answer it on your own. And so the answer to this is that we want to use our Q equals M times C times delta T. And so remember, the M is the 7.77 grams. The C, the specific heat, is 4.184 joules over grams Celsius. And the change in temperature will just be our final temperature minus our initial temperature. And so if we input these into our equation, we get this. And then when we solve it, we end up finding out that it is 133 joules. And this is in 3 significant figures because our mass and our temperatures were both at 3 significant figures. And so that is the fewest number of sig figs. We can also use this equation to predict what temperature something will be after transferring a certain amount of heat into it. So say we have a silver bar with a mass of 284 grams at an initial temperature of 25.3 degrees Celsius, and it absorbs 1.13 kilojoules of heat. We want to know what the final temperature of the bar of silver is if the specific heat of silver is 0.235 joules over grams Celsius. So again, I would encourage you to pause the video and try this on your own. And so the way to approach this, so the first thing we'll want to do is actually convert the kilojoules into joules. So we use this, that gives us the 1130 joules. Then we want to plug that into our Q equals MC delta T. So this 1130 joules is our Q, this 284 grams is our M, this 0.235 joules over grams Celsius is our C. Then we have the delta T here, but we're trying to find what this final temperature is. So we need to solve for this final temperature right here. And so the first thing to do is just multiply this grams times the C right here, which is our specific heat. And so we would see that the grams will cancel out and we end up with 66.7 joules over degree Celsius. And so then we end up with this right here. What we want to do is take our 66.7 joules over degrees Celsius and distribute that into here. And so we'd be multiplying it by this number and multiplying it by this T sub F. So we end up with this right here. And then we want to we're trying to get T sub F by itself. So the first thing we can do is just add the 1690 joules to both sides like this so that we end up with this right here. So then we have this 2820 joules equals 66.7 joules over degrees Celsius times our T sub F. We can divide both sides by the 66.7 joules over degrees Celsius to get T sub F by itself. And so we end up with this. And so that means the final temperature after absorbing that amount of heat will be 42.3 degrees Celsius. And that should make sense. We're going from a lower temperature to a higher temperature when the silver is actually absorbing heat. So absorbing heat should increase the temperature. Another way that's important for thinking about energy is with our nutrition. So, for instance, carbohydrates is sort of our main source of energy, but we can also get it from fats and proteins. And so, what are the units for the amount of energy in food? We've been talking about joules mostly this whole time, but when you look at the nutrition facts on something, it's usually in calories. And so, this is typically done in calories, which are actually kilocalories. And so what we want to do is pay attention to the case of the C. So an uppercase C actually is talking about a kilocalorie, where a lowercase c is talking about a calorie. So remember, we said that 1 calorie, this uppercase calorie here, is going to be equal to 4.184 kilojoules, whereas we saw before that the lowercase c calorie was equal to 4.184 joules. So again, you want to make sure that you're paying attention to the case, whether it's uppercase or lowercase, of the C in calories. And so remember, carbohydrates, fats, and proteins provide energy for the body to do work. We're using the calories for our units for this. And so the energy values for carbs, fats, and proteins have been determined and can be used to estimate the energy value of food. So carbohydrates has 17.0 kilojoules per grams, so we'll call that 4.00 capital C calories per gram of carbohydrates. Fats, it's 9.00 capital C calories per gram, and protein, it's 4.00 capital C calories per gram. So for instance, if we want to solve a problem using this, how much energy in capital C calories can be obtained from a food that contains 4 grams of fat, 19 grams of carbohydrates, and 2 grams of protein. So you should pause this and try to work through this on your own. And so the answer to this is that the first thing we want to do is actually convert these from the grams of these nutrients to the calories. So for fat, we would just take the 4 grams of fat, multiply it by the 9 calories per gram of fat. The grams will cancel out. We get our calories from it. It's 36.0 calories from fat. Then with the carbohydrates, it's 19 times the 4 calories per grams of carbs. That gives us 76.0 calories from carbohydrates. Again, notice we're using the capital C cal on here. So that's actually the kilocalories, so the capital C calorie. Then the 2 grams of protein times the 4 calories per gram of protein gives us the 8 calories from proteins. And so to get the total amount, we want to add all of these up. And what we will find is that this would actually be 120, and this should actually be 120.0 calories, because our significant figures here, we have the fewest past the decimal as 1 past the decimal. So this right here is actually a mistake. It should be 120.0 calories total. Since remember, when we're adding, we want to go the number of places past the decimal that's the fewest used in our problem, where this one we have 1 past the decimal as the fewest in our problem. So again, this is a mistake. It should be 120.0 calories total. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.